Hey guys, so in the last video we discussed about what is dimensionality reduction and how it really works and why should we use a technique of principal component analysis to reduce the dimensions. I'll give you a just quick recap to understand what is this concept called dimensionality reduction stands for and how do we use this principal component analysis. So in this video we will see the demo of PCA, how it looks like and how to implement the same. But before we jump in, just a quick recap. A principal component analysis is one of the technique which works like a magical scissor that can cut through the complex data and reveal the hidden patterns in your data. In simple words, the idea of PCA is very simple. It is to reduce the number of variables of the dataset, reduce the number of features, reduce the number of columns while preserving as much information as possible, right? This is what we discussed in the last video. And we have also seen how it really works. So if you haven't watched that video, please go through the PCA part 1 video first and jump to this video. So stay tuned and make sure to watch this video till the end and let's get started. Hey guys, welcome to AI with AI. This side Asif Imnad. Okay, so let's jump to the demo part for now. By the way, I have uploaded all these demos on our Git repository. The link of the Git repository you can find in the comment box below. So we have seen demos on feature engineering, regression, classification, clustering, anomaly detection, PCA, all for free. We have spent a lot of time, lot of efforts in creating these demos and videos for you for free. If you love our efforts, just do one thing, like and subscribe. Share this video with your friends and the colleagues as much as possible. Let's first understand how this PCA works and then we'll apply this PCA on one of the popular dataset, which is iris dataset. So let's start with learning PCA first. Alright, first thing first, let's import the libraries. We want to plot the data. That's why matplotlib as plt, numpy for some numerical operations and cborn again to plot some advanced graphs. Shift enter to execute. I'm generating some random data set here so that it becomes easier for us to plot and easier for us to visualize. We are not importing any data set here. We are generating random data set so that we just understand the concept of PCA, how it looks like and how it really works. Okay, so let's execute and this is how the data set looks like. In 2 dimensions, we have plotted the data. Data is very much linear. Now, after applying PCA, we want to reduce the dimensions. So currently we have only 2 dimensions, 2 features and 200 data sets, 200 rows, right? We want to reduce the features. Let's reduce it from 2 to 1 by applying PCA. And how do we do that? For that, we need to import PCA from sklearn library and we initialize PCA and the parameter, which is the most important parameter that we need to specify here, is the number of components. The number of components are currently we are considering as 2. The original is also 2. Later on, we'll see the effect after reducing these components. Okay, so currently let's just initialize PCA for 2 components and PCA.fit, right? In every machine learning algorithm, it's very easy. Import, initialize, fit, and then predict, right? But one thing to note here, PCA is not the machine learning prediction algorithm. It doesn't predict anything. It is a data pre-processing algorithm. It processes the data. It is a feature extraction algorithm, right? Before providing your data to the machine learning. So that's why we will not have any predict method on PCA. Let's execute this. And here in this cell, what we're doing, we are just drawing those PC1 and PC2 lines along the data to understand how does the PC1 and PC2 line looks like, right? PC1 line will be the best fit line over the data and PC2 line will be the perpendicular to the PC1 line, which will show the variance in the data, right? So let's see how it looks like. After executing visualization line, PC1 and PC2 lines are drawn over the data. This is how it looks like. Now we can try to reduce the dimension. Let's convert this 2D to 1D by again using PCA. Mentioning components is equal to 1. I want to transform the model.fit transform and the input data. Let's look at the original shape and after transforming the data, how many columns that we have now. So if I execute this, you can see the original shape looks something like this. So 2 features and 200 rows. And after dimensionality reduction, you can see 1 feature, which is 1 column and 200 rows, right? So dimensions are reduced. But how do I see this? How do I plot this data? To plot this data, just for understanding purpose, I'm using one of the method called inverse transform. I want to convert that one dimension again back to the two dimension. I can plot the data and I can see how it looks like, right? What I'm plotting here, this data, the new transform data, right, after performing PCA. So if you see here, model dot inverse transform x new and plot that data. Do you see this? The blurred data points which you see behind are the original data set, and these data points which are relatively darker is the PC1 data. Isn't it amazing, right? And this is what we discussed in the first video, that how principal component analysis really works. Okay, before we proceed and discuss in detail, if you are new here, don't forget to hit that subscribe button and the bell icon so that you won't miss our latest videos on AI. We see you are watching our videos, but 90% are not yet subscribed. We put lot of efforts creating these videos for you free. Keep us motivated by liking and subscribing, so YouTube algorithm will also help us reach more audience. So did you subscribe and like? Thank you. Going to the second demo, this was just to show you how PCA works, how to use PCA, how to import, and how to perform inverse transform to visualize the data. Let's go to the second demo and actually perform principal component analysis on the actual dataset, which is iris dataset. This is the most famous classification problem in the machine learning. There are three species of iris flowers. When the flower is given, we need to predict what class this flower belongs to, whether the flower belongs to Setosa, versicolor, or the Virginica, right? Given the data, what is the data given? Data is given something like this in the form of table. The sepal length, which is the bottom part of this flower, sepal length and sepal width is given. Similarly, petal length and petal width is given in the table. So based on these dimensions, based on this data, we need to predict what that class, what that flower belongs to, Setosa, versicolor, or the Virginica. We discussed this multiple times in our previous videos, right? Let's perform PCA on this dataset. As usual, very first thing, import the dataset. What we are importing: pandas for data frame, matplotlib for plotting data, seaborn for advanced plots, numpy for performing numerical operations, and sklearn obviously for machine learning algorithms and to work with the datasets currently. Here we are loading the iris dataset, which is available in the scikit learn library itself, which we imported here, and we are converting that dataset into the data frame so that I can print it and work with the dataset, right? So data frame is nothing but the data in the form of rows and columns, because of which it becomes easier for us to visualize and handle the data. And I'm printing the first 5 rows of this data by using df.head. You can see we have considered certain features, certain columns here, and that's how it is showing us the data in the table here. Let's see the count of the data for the target, which is Y column. So total number of species that we have: for 0 it is 50, 1 it is 50, and 2 it is 50. So equal distribution of Setosa, versicolor, and Virginica, right? So class 0, 1, 2 is nothing but Setosa, versicolor, and Virginica. Definitely machine learning doesn't understand categorical data, right? So that's why it is in numbers. 0 is for Setosa, 1 is for versicolor, and 2 is for Virginica. Let's plot this data using matplotlib, and the plot that we want to use is the scatter plot. So that's why I'm importing matplotlib and the seaborn as SNS, and we are plotting the scatter plot here by mapping certain features. I want to consider only these two columns data first: sepal length, sepal width, because I can draw only two-dimensional data, right? You can consider petal length and petal width as well if you want. For which column? For this column. Which data set? The data set which we converted into the data frame. This is the height of the graph, and add the legends. Let's print the data and see how it looks like. Let's plot the data, and this is how it looks like. You can see that the blue is very much different, that is Setosa is very much separable, whereas orange, I think it's versicolor, and green is Virginica. Setosa, versicolor, and Virginica, right? For versicolor and Virginica, there is a lot of confusion, right? So there is a very much mix in between these. So classifying versicolor and Virginica flower becomes difficult for us and difficult for machine learning as well to classify this data, right? Whereas for classifying type 1, it is much easier. Setosa can be classified very easily by providing sepal length and sepal width. That's what I understand by looking at this plot currently. Okay, our aim is to apply PCA. So let's apply PCA on this. We already learned what is PCA. So on this data set, we are gonna put PC1 and PC2, and let's see how it goes. We are loading the data set again, converting the data into X and Y, because I only want to process input and I don't want to consider the target for now, right? I'm using PCA. The original number of components, definitely we have 5, right? So if you see sepal length, sepal width, petal width, and the target. So total 5 components we have. After converting into X, we have 4. We want to reduce the dimensions. That's why I'm providing number of components is equal to 2. And PCA.fit transform to reduce the dimensions. Let's execute this. And finally, all we want to do is plot the 2-dimensional data. Plot this data, which is PC1 and PC2 data. And for that, what we are using again here is the scatter plot. We are using red, blue, and green. And these are the markers using for loop to plot the scatter plot for all these markers. Added the labels and show the plot. Okay, so this is how the plot looks like after converting your original data to the principal component analysis. So you see the Setosa type, the first data type 0 is very much separable, and the cross is versicolor, which is again better than the previous plot, right? After converting PCA, you can see some separation there between the data. If you look at this graph, this plot here, there is very much mix, and it is very difficult for us to draw a line and do the classification for this data set. But if you observe after applying PCA on the same data set, this is how the data looks like. So the accuracy on this data set after performing PCA will be more better than original data. That's what we can conclude from this discussion. So after applying PCA, I will have the better accuracy because visually I can see there is more separation between different type of data sets. And that's the benefit of using PCA in feature engineering in machine learning techniques. For sure, I'll show you what is the effect of PCA on the accuracy of the data in the next demo. Currently, this is it for now. In the next video, we'll see the actual demo with the real dataset and perform PCA, and also see what is the effect of PCA on the accuracy of the machine learning model. Alright, and that's how we come to an end of this video. If you have any questions regarding the same, let us know in the comment below. If you found this video helpful, please subscribe to my channel and hit the like button, and don't forget to share this video with your friends and the colleagues. Thanks for watching. See you again next time. Till then, take care and bye-bye.